Today we have a visitor from Poland. I'm not talking about Wojciech, by the way. No, I'm talking about Professor Szymon Malinowski. Simon's been a frequent visitor to NCAR for the last 30 years or so, we've discovered. And so Simon's the director of the Institute of Geophysics at the University of Warsaw, and since 2016, and since 2002, he's been a professor at the University of Warsaw in the Atmospheric Physics Department. Szymon has published widely on the physics of clouds and precipitation, atmospheric turbulence, numerical modeling of atmospheric flows, and atmospheric airborne measurements, and remote sensing. About covers it, right? I think, right?
We are small, we have to do everything.
You have to do everything, okay. Just last year, Szymon was awarded by the Polish Science Foundation the Marcej W. Grabski Award for actions for the understanding of science and society, and it's become a source of information on climate change for Poland. So today's talk: turbulence in clouds, non-stationary, non-uniform, anisotropic, and intermittent. What can we do?
Thank you very much for your introduction. Thank you for hosting me here. And it's completely different talk than I was supposed to give, but when I started to prepare this talk, I found that there is too many small letters, equations, and so on. So I will talk more about physics and more about the phenomena and more about what we have measured and how to deal with it. And what, if you want to find the details of the methods, they are in the papers which are listed here. So what is turbulence? The first, turbulence has no good definition. I don't know whether I can say a joke, but I have learned from my professor who taught me about turbulence that turbulence has something to do with pornography. There is no exact definition, but when you look at it, you know whether it's turbulence or not.
That's the fastest
So for atmospheric modelers, it's something subgrid, generally. Whatever is subgrid, they usually refer as turbulence. For pilots and passengers, you know, when they feel some shaking during the flight, they encounter turbulence. Okay. For fluid dynamics, it's motion characterized by chaotic changes in pressure and flow velocity. And in this talk, I will talk about what we have measured flying in clouds and around them. We're focused on scales of hundreds of meters and below. And this process is cause mixing, cause transport, and so on. And they are important to understand what's going in clouds and what's going on in the atmosphere. And we'll focus on this smaller part of turbulence, means turbulence cascade in the atmospheric boundary layer in clouds around. There is also some clear sky turbulence and whatever. And I will talk about some findings from 3 airborne research campaigns. There will be something about modeling, but not too much. And there were three research campaigns which we have used small, slowly flying aircraft, which allows for pretty good resolution of the measurements, spatial resolution of the measurement. One was physics of the stratocumulus stop when we are flying with a small aircraft in the stratocumulus close to California coast, and it was 2008. The second campaign used a helicopter-borne platform at Azores, and we are flying in northeastern Atlantic, close to atmospheric radiation program site Graciosa, also mostly in stratocumulus. And the last was from already 3 years ago, Eureka, when we used to fly through warm cumulus clouds. And I will start from post. The idea was to address the problem of entrainment into stratocumulus, which is still not fully understood and not fully resolved. And the majority of our flights were just a kind of porpoising across the top of the cloud. Inversion, cloud top, somewhere to the cloud layer, but not very deep, just to characterize the properties of microphysics, but also of turbulence in the cloud top region. So these are some examples. I will focus of two cases from post, which we call typical and non-typical stratocumulus. The depth of the cloud is here in gray on this plot, and close to the cloud top is this region we were focused mostly. We call it entrainment interfacial layer, but we subdivided this layer into two elements, since usually people account for cloud top interfacial layer looking at the very cloud of the top. But we have focused also on the turbulence in the inversion, very stable inversion having turbulence above. So we have measured it. And below, the layer we call below is cloud top mixing sublayer. So generally, imagine the aircraft, which is going like this through these two layers, trying to measure whatever can. We will focus on liquid water content, temperature, and three components of the velocity. So here you have two examples of the aircraft penetrating down to the cloud. On the lowest panels, you can see the trajectory, the altitude of the aircraft. It's on the right-hand side of the panel, which the aircraft goes down, let us say 2 degrees slope into the cloud, so there is much more horizontal than vertical. Nevertheless, it's in time. You see liquid water content, so you see the first touch of the cloud is the cloud of the top level of this cloud top mixing sublayer. But above, if you see the three velocity components in the uppermost part of the plot, you can see that above the cloud, you can see already some substantial fluctuations of velocity which occur. And you already see a kind of fluctuations of temperature and humidity in this layer, despite the fact that this is above a cloud. So it's a kind of signature that there is some turbulence there. So we tried to analyze, since these data were not usual. Usually you collect data in horizontal cross sections. And we had this slant trajectories. And we had to stratify the data, somehow cut it into pieces to have the segments which can be attributed to the given level in the cloud. So it took a while to find a kind of objective division based on measured properties of dynamics and thermodynamics to propose an algorithm, since you can put every lines by eye, but we wanted to be objective to build a kind of statistics of turbulence and properties clouds across these layers, which can be objectively distinguished. So I will not go into detail, but we have found such a division, and generally we found the typical thickness of this inversion layer at the top of the cloud is in the range of 15 to 35 meters. So it's pretty small if you compare it to typical resolution of numerical modeling, even larger dissimulation. And this cloud top mixing sublayer is twice as thick, typically. And first we estimated gradient or bulk Richardson number across these layers. And there are many penetrations. You know, each bar here is a kind of, no, this is the statistics of penetration, the value of gradient Richardson number. Somewhere between 0.25 and 1, you consider the marginally unstable turbulence. So the majority in both layers is the marginally unstable turbulence. And we had resolution good enough to estimate from power spectra and from second order structure functions. We made these estimates independently. TKE dissipation. So the TKE dissipation epsilon, you can find the information about the paper, but we use this, you know, TKE dissipation to estimate some characteristic scales. Since across these layers, we've seen substantial shear, which is S here in this equations, or stability, since inversion is very stable, and this cloud top appeared to be slightly stable, so stability. And we estimated so-called Korsin and Osmidov numbers. So these are a kind of numbers which refer to the state below the scales, characteristic scales. Turbulence can be considered isotropic. But above the scales, this turbulence is being elongated by a shear. Turbulent eddies are being either elongated by a shear or damped in vertical by buoyancy. So as you can see, in this turbulent inversion sublayers, these numbers are pretty small. So all the eddies of 1 meter and more are affected by this buoyancy and shear effects. So they are elongated. So they are completely different in horizontal than in vertical. In cloud top mixing sublayer, we also had pretty small numbers for these scales. So typically in turbulent inversion, it was 30 centimeters and about 3 meters in cloud top mixing sublayers. So this is an indication that turbulence in this region is very, very anisotropic. At least these scales we resolve generally, making measurements and making our models. Okay, so what have we done? There is an example. We tried to estimate velocity variances in one or second flight, different kinds of stratocumulus in horizontal directions and in vertical directions across the layers. And generally in through troposphere, there is almost no turbulence, so these variances are negligible. If you go deeper to if you are in this turbulent inversion sublayer, in the inversion, you have significant anisotropy and even more anisotropy just below the cloud top in the cloud. Your velocity variances differ very much in horizontal and in vertical. And of course, this is reasonable due to this shear and buoyancy effects. So generally, your turbulent eddies look like this. Small eddies can be isotropic. Large eddies are very anisotropic due to shear and due to buoyancy effects. And this is a kind of example of the study. We tried to make a kind of, since within this project, we tried to estimate different mechanisms of entrainment, we did some large eddy simulations. And what we found amazing in the simulations, that all the large, so-called large eddy simulations, which have the proper anisotropy ratio of grid boxes, provided more or less reasonable entrainment and behavior of the clouds. If you went to higher resolution without keeping this anisotropy, you got in problem. Clouds dissolve very quickly. You know, this pretty thin layers across which you can mix air efficiently led to the dissipation of cumulus clouds. And yeah, these are two illustrations of you know, some snapshots of the velocity field. And you see that in, let us say, resolution 15 by 15 meters, you got a kind of symmetric eddies in the cloud top layer, which were much more efficient in vertical mixing than this eddies here. And this anisotropy of the eddies is also due to the fact of, you know, that they are on the anisotropic grid. So you can get a right entrainment in your stratocumulus, in your simulations, due to good reasons that you represent properly what's going on the cloud top, or by wrong reasons, that by chance you have the right aspect ratio of your network. What we have checked then later, we were interested in this anisotropy, and we tried to kind of check how this anisotropy changes with the scale close to the cloud top. And this is plot which summarizes two numerical simulations, two sets of numerical simulations. One P13 is this post-13 flight, and D1 is DICOM's one flight in stratocumulus. And these are, you know, we call it spectral anisotropy, just a ratio of amplitudes corresponding to the different wavelengths. You have wavelengths on a horizontal axis. And what is here with these dots, they are estimates from the experimental data. So you can see that you can see that the spectral anisotropy is positive when horizontal energy in horizontal modes is larger than energy in the vertical modes, and you can see that this anisotropy and the opposite is for some scales. You can see that for some scales, especially for DICOM's one highly entraining flight, this P13 was weakly entraining flight. At some scales, you have some anisotropy in the second direction, spectral anisotropy in the second direction, which corresponds to this cloud holes and formation of downdrafts in clouds. Yes?
Just a quick question. What is Z sub t in that normalization?
One more thing. ZT average. I think it was averaged by the kind of a depth of the layer. Or the depth of the boundary layer. Sorry. So in large scales, you have, you know, these convective structures and large sails. If you go to the scales of a fraction of the depth of the boundary layer, you have these downdrafts, and then you are close to the cloud top. And yeah, it was the depth of the boundary layer, and in the scales lower, you have again this anisotropy, but to this buoyancy and shear effect. the large-scale anisotropy is just to the fact that you are in the distances which are much larger than the depth of the boundary layer. So what we have learned from POST, that there is a lot of anisotropic turbulence due to shear and static stability close to the top of STBL, stratocumulus topped boundary layer, that anisotropic turbulence affects in anisotropic transport, which explains problem with modeling interpretation of entrainment. And this anisotropy can be characterized even using standard measures like velocity variances or spectra. And this anisotropy can be scale dependent. Okay, the second campaign was Azores, where we had partly similar stamping strategy. We had a device which was hooked at 150 meters tow below the helicopter, so it's absolutely not affected by downwash. There was also some device to measure radiative properties of the clouds. We're not involved in, and we are putting it into the stratocumulus, and also we made a kind of much steeper, porpoises, and we made also some horizontal legs. What was the advantage is that we had that's it. The ultrasonic anemometer, which had a resolution, spatial resolution of the order of 20 centimeters, and with a relatively low horizontal speed of the order between 15 and 20 meters per second, we were able to make turbulence measurements with very high resolution. I'm not mentioning now, I will mention the last, we're using also high frequency temperature sensors made in Warsaw, but I will show examples from the last plot. We will focus on turbulence. And having these instruments, having experience with POST, we started to develop tools to characterize turbulence in a bit wider way than it is usually performed after the field experiments. So, for instance, we had some problems with the sonic. So we had a problem with transversal velocity component. Nevertheless, we substituted a kind of turbulence kinetic energy like this. With some flights where everything was okay, we have checked that it works pretty well. And you might have here, again, some profiles of, there are, again, two cases, one with so-called coupled stratocumulus topped boundary layer. Coupled means that below the cloud top, we did not observe much variability in the properties below. And it's typically explained that there are some eddies of the scales of the depth of the whole boundary layer, which led to mixing. Despite this mixing, you can see on the top that first, across the whole layer depth, we had significant anisotropy in the fluctuations, horizontal and vertical. The second thing, we had some profile of turbulence kinetic energy with pretty high values of turbulence kinetic energy in the middle of the boundary layer. And we had in the second cloud, where we had a kind of decoupled layer above the surface, the lower part of the boundary layer, we had much more variability in velocity variances. You can see that the vertical velocity at this layer were probably very, very close to zero. And we had also despite the fact that TKE in this level layer was pretty high. So we started to analyze turbulence in much more details. So first we again used power spectra and the second order structure function. This is an example of the second order structure function from one of the segments. To remind you, the second order structure functions should scale with the power 2/3. And it corresponds to -5/3 spectra in the wave number space. So with parts of the flights where we made the vertical profiles, we plotted, these profiles, but with the kind of segments, we had a kind of horizontal legs. We also calculated this estimated turbulence dissipation rates. As you can see, the results matched pretty well. Generally, we had much less turbulence and much less dissipation in the decoupled case. And what is shown in the both right panels is a kind of by vertical dashed line, you see the values 2/3. The theoretical slope of the second order structure function. Theoretical slope of the structure functions. And you see the actual, slopes on the segments larger than several integral scales. I will go to integral scales in a moment. And usually you can see that across the upper part of the boundary layer, we have very bad fit. So the slope of the structure function is much lower, 0.2, 0.4, than 2/3, 0.66. So it means that this turbulence is not close to the Kolmogorov turbulence. We can, again, try to estimate dissipation rate, but generally fitting slope is less. So in terms of power spectra, we should have also a kind of less steep power spectra. So maybe I will skip it and we'll go to the length scales. We started to think about very accurate, division of our data into the segments to make a proper Reynolds averaging. Since generally, when you fly in such situations like this, you cannot assume horizontal homogeneity. Typically, if you make a kind of measurements in a boundary layer by the aircraft or whatever, and especially if you measure fluxes, the longer you fly over uniform region, the better. You have the better statistics. But since we had such different turbulences in different layers, so we tried to make a kind of Reynolds averaging appropriate to each segment or each fragment of the flight. So to make this Reynolds averaging proper, we had to estimate the integral scale of the turbulence and to measure along several integral scales. So LU, this is, correlation function of the velocity fluctuations on the top. And integral scale is by definition a kind of integral from this correlation function. And it allows to estimate the integral scale of the turbulence. In fact, you don't go to infinity, you go to some to some given number, check whether the integral changes or not. But what we have got from these integral scales, we found them of the order of 100 meters. So it's much less than the depth of the boundary layer. It's much less than the circulations which mix across the boundary layer. And if you think in terms of Kolmogorov turbulence, not exactly Kolmogorov, but cascading down turbulence from integral scale down the scales, what is above is a kind of mixture of turbulence and eddies and some other stuff. We were also able to estimate Taylor microscales and Kolmogorov microscale, and it's everywhere, everything in the plot. But what is most important here is that you are in this integral scales of the order of 100 meters. Your Taylor microscale, at which the turbulence should be kind of generic and isotropic and whatever, is a few tenths of centimeters, half meter, 1 meter. And yes, the Kolmogorov microscale is around 2 millimeters independently. So this is a range of scales we consider, the turbulence cascade. So from 100 meters to 2 millimeters. We have also measured anisotropy. Again, we used a kind of a different, we also measured anisotropy by the ratio of vertical and horizontal velocity variances. But since we estimated turbulent kinetic energy dissipation rate from vertical velocity fluctuations and horizontal velocity fluctuations independently, and there were some differences between them, we just have plotted them. The differences are not that big, but generally the ratio, even if you, is of the factor of 0.7 or 0.8. And of course, it's feasible since, you make these estimates from the power spectra. You do not measure the TK dissipation rate in a dissipation range, but you estimate it from either slope of the power spectra or slope of the structure function. And this biggest eddies, which contain energy, has, this effect on slope.
I have a question.
Yes?
So on that left plot there seems to be a vertical oscillation in that data. Is there anything physically significant about it? That seems to be a regular scale in the plot of CW.
Yes, this was just a profile. When the helicopter took off or made a kind of a vertical profile, this is a kind of so we take some selection on the profile and make it in a constant line. It's a kind of moving window.
Right.
Okay?
But I'm looking at the red line that's oscillating. Is that?
Yes, they are on the left-hand side, they are out of phase.
Okay, so what's
I don't know why yet.
Oh, okay. So there's some
on the right-hand side, it's not that obvious, but yes, I've noticed it, and it happens several times.
Okay, you think that there's something physical there.
Yeah. But till now, I don't know what is it. Yeah.
Okay.
So the first lessons from Azores, that there is a lot of anisotropic turbulence, not only close to the cloud top, but across the boundary layer depth. That these integral scales below which you should consider standard Kolmogorov cascade of the order of 100 meters, not few hundred meters. And it's consistent in other data as well. And there are differences in turbulence across the layers of the boundary layer. So the next thing we started to work with, based on this data, is a kind of, this is a kind of horizontal leg through the part of the boundary layer on a distance of 5 minutes. So 300 seconds at 20 meters per second, it's 6 kilometers, yes. Variability of vertical velocity and our estimates of TK dissipation rate, which vary on this distance. And estimates of scales, characteristic velocity scale, which you can see here, and it's related to variance. So kinetic energy is of turbulence is, root square of sum of velocity variances. So it varies, maybe not that much, but by 30%. And the same is with the integral length scale. In this particular example, it's even less than we had before. And the question is the following: whether in this horizontal direction the turbulence is isotropic, and maybe we can distinguish between some regions where there's produced or being dissipated or whatever. And if you look at the standard plot of the energy spectrum, this is a kind of typical picture you might have in mind. Every one of us had seen such a picture with turbulence energy cascade and minus 5/3 slope. If you imagine what happens when you start to produce more turbulence, if you start to produce this more turbulence in the large scales, then the amplitude of your wave numbers in the large scales should grow before, this excess production of turbulence by the energy flux downscale goes down. Yes? And if you stop produce your turbulence, or you produce less than it is dissipated, then you have the opposite effect on the spectrum. Of course, I'm saying it it was a great idea, whatever. We found some things in the literature. This is a kind of artificial turbulence we generated, but now I have to tell you the story about from the measurements in wind tunnels, and we read a lot of literature, and generally you can, instead of using for the equilibrium turbulence, if you make some scaling, the ratio of integral scale to the velocity scale, it means this which is proportional to TKE. So the velocities of the largest eddies to third power multiplied by the dissipation rate is constant. So you can what some colleagues, Christos Vassilikos and other, tested in a wind tunnel, they were making the measurement along the pretty long wind tunnel. There was a turbulence generating grid in the front of the wind tunnel, and they made successive measurements of turbulence in longer and longer distance from the place it was generated. And they found a kind of scaling that if you have a Reynolds number at the entry area 0, and and then you calculate Taylor Reynolds microscale Reynolds number, that this C epsilon, which used to be constant in stationary turbulence, in the decaying turbulence, since the turbulence decays along the wind tunnel, scales in a different way. So Bose and Rubinstein proposed a correction to Kolmogorov scaling just by expanding, the Kolmogorov scaling into Taylor series, and they proposed the correction which accounts for this effect of the rate of change of you see epsilon dot is rate of change of dissipation or rate of change of transport downscale. Yes, in stationary turbulence, it's equal. So with Bose and Rubinstein, scaling, we could check whether this C epsilon is constant or whether it is not constant in our data. So we could estimate, TK dissipation rate. We could estimate scales, velocity scales, and integral scale, and just put it into the Taylor formula and check whether C epsilon is equal to the theoretical one or greater or smaller. According to this theory, CE epsilon should be greater as you have dissipation prevailing, could be smaller than this equilibrium value for dissipation production, and of course equal to the stationary statistics. So this is an example from one horizontal flight and segment, and from the second horizontal segment, when step after step, using Reynolds averaging after, I think, 5 integral scales, we made these estimates of C epsilon. And what can you see? That, for instance, for this flight, we had a constant production of turbulent kinetic energy, since our C epsilon is smaller than the equilibrium one. Equilibrium is this black line. In the second flight, we have such a situation that for some part of the flight we are in equilibrium. In the next part, we are in the region when there is decaying turbulence, and in the third region, that there is production of turbulence, and sections are pretty different. So we try to divide some segments of flights. This is from one flight and from the second, just such a segments of few integral lengths, and we found, that if we have a C epsilon constant through the we plotted in with respect to the Taylor microscale Reynolds number, and we have checked whether this scaling. We found segments which pretty nice fit along the constant, means a kind of stationary turbulence. We have found segments in these flights where we have the production and we have dissipation. So it fits the theoretical lines. So I will skip another one, since it's similar but a kind of a different check. But what is a funny story is that we can distinguish when we fly with the aircraft and we fly through the turbulent region whether the turbulence is being produced here, or is a kind of stationary state, or is being dissipated by whatever. So I think it's nice information which now can be used and verified with numerical models, and it's very sensitive to the fact that there is a dependence to the third power of velocity scale. So really, if there are some changes of epsilon and L, but large, this characteristic velocity scale, so this is this scale in which you have this production or diminishing production of turbulence kinetic energy. This is in the third power here. So this method is pretty sensitive to these changes in production and dissipation. And one more byproduct, maybe I will skip, maybe I will not skip. We have, when we are solving looking for different methods of estimating TKE dissipation rate, we got to some methods which are described in the literature, but which are not usually used in the atmospheric data. And one of them is based on so-called zero crossings. if you have fully resolved turbulence signals, and when you subtract the mean velocity, your fluctuations cross zero. And turbulent kinetic energy dissipation rate is proportional to the density of the zero crossings. There is a theory developed by Srinivasan over earlier mathematical works, and under some assumptions you can find it. But we do not have a fully resolved turbulence, but we can somehow downscale our measurements, which resolve scales, let us say, a few meters and up, to the take some factor, and we can check whether our density of crossings corresponds to the theoretical one, to the theoretical ones. And since you are flying, sometimes when you are flying through clouds, you fly through turbulent, non-turbulent, turbulent, non-turbulent region, you can get a kind of external intermittency, means what fraction of your flight is segment of the flight is turbulent and non-turbulent, looking by this measure. And again, it's pretty straightforward. If you are in laminar region, you have no zero crossings or one crossings due to some tendency. Next, Eureka atomic. I have added something to this part of the presentation after we chat with Don Lenshaw today. So this was the idea of the experiment, measurements in warm clouds, and we are flying on the Twin Otter, British Twin Otter aircraft, which was supposed to fly through clouds. It's not stratocumulus like previous case, but it's warm cumulus east of Barbados. Three years ago, huge campaign, Eureka Atomic. There was American part was called Atomic, European part was called Eureka, due to different foundings and so on. Nevertheless, it was coordinated. And I will not talk about the whole campaign, but just about our measurements in clouds. And by the very strange series of events, we landed in this British aircraft. We were supposed to fly on Sirpas Twin Otter, and we have been already founded to measure the temperature fluctuations in a very small scale. And to do this, we had to make our sensor as small as possible to fit the turbulence probe and to be completely autonomous. We could not connect to any aircraft systems. We are recording temperature fluctuations at 20 kilohertz we fly. So you see our temperature sensor, which is 2.5 micron wire and about 3 millimeters length, which was set on the top of a 9-hole probe, which measured turbulence. And we have a pretty unique set of the temperature fluctuations and turbulence fluctuations from this experiment. Still, there are some issues not in our sensor, but in this 9-hole probe. Just to show you how the flight, this is a fragment of one of the flights, when you have, altitude of the aircraft by gray, estimates of TKE along the flight, so you can see it varies a lot. You have regions of red or blue. Blue is low TKE, red is high TKE. This is the external. In the middle, you have a kind of temperature measure, so you see also enormous fluctuations of temperature. And just I promised to show our temperature sensor capabilities. So this is one of the plots from inside the cloud. We have also some flights in the boundary layer. Generally, we are able to detect, filaments of few centimeters thickness during mixing. And generally, since this sensor is really fast and its length is 3 millimeters, So we are very close to the Kolmogorov scale. So in principle, we could measure the dissipation directly, but not dissipation of the velocity, but the dissipation of temperature. But the first thing is that you can see in these plots that there is a lot of variability of turbulence and around clouds and so on. So again, the question is the following. We are now working, since it's something with what we do, we could somehow stratify the data from the boundary layer, assuming some horizontal homogeneity, more or less, to make these cloud penetrations. But generally, if you fly horizontally through cumulus clouds, the question is, what is cloud? Of course, you can have it with a liquid water content. But there is a lot of dynamics around the cloud. So how to set a right, numbers where is the edge of this dynamical system? How to measure? How, again, to stratify your data in, let us say, outer turbulence, inner turbulence, cloud edge. On the beginning, we did not have liquid water content systems, and we started to work with so-called recurrence quantification analysis. This is a kind of analysis which was introduced to characterize dynamical systems. And generally, in dynamical systems, you can imagine you have phase space, let us say three-dimensional phase space, and you have each point in this phase space can be represented by a vector starting from 0 and ending at this point. And this recurrence quantification analysis is a kind of measure how often this vector in the first phase space gets into more or less the same region of the phase space, so into the same conditions. So we constructed such a phase space in a way, yes, I'm finishing, 2 plots more. In a way that we are using, we consider what is important. For turbulence, mixing is important, so it can be represented by temperature fluctuations. Turbulent kinetic energy is important. And since we are in cumulus clouds, vertical velocity is important. So we constructed, our phase space around these values. Later, we have liquid water content, which is shaded by gray. And this is one of the measures, so-called laminarity, applied to the whole vector we constructed and to each component. And we think that taking low threshold on this laminarity is a perfect way to find, first the regions of turbulence, and then if you look for the specific properties of the turbulence which are prevailing in each region. So this is just the very preliminary. The second thing, we have taken the advantage of our temperature sensor to estimate temperature dissipation rate. Temperature dissipation rate is estimated by the temperature difference in the next steps, by the squared to the mean to the average squared temperature variance, in fact. So you can see a lot of intermittency, internal intermittency. You can see that this normalized dissipation rate varies very much. And we didn't do so much so far, but we have found that if we make a kind of histograms of this normalized temperature dissipation rate around clouds, every kind of colored here line is one cloud. We have a kind of scaling, I don't know why, but there is 1/3 scaling in the histogram to the certain value, and above there are various things. So we have some interesting results. We do not understand them yet. We think that using this recurrence quantification analysis will allow us to, characterize turbulence in various regions around clouds using these methods we developed earlier. And what is the final message? If you try to understand turbulence in highly variable region, this is not the case that longer averaging means better. Since you are not in the stationary region, so you have to be very careful about, selecting segments for averaging. To do this, you have to determine integral length scales based on autocorrelations. Turbulence is inhomogeneous, so you should average after several integral length scales, not about hundreds. And then you have a tool to quantify, your turbulence in much more detail than we usually do flying through clouds. So we can quantify velocity variances, TKA, dissipation rate, all relevant scales, and these other characteristics I was talking about. And the final question is the following. Turbulence or turbulences? Since we had different regions of different properties of turbulence. And I think that we have to work on this. Thank you very much.
Okay, the paper is now open for questions, comments. Yes.
Yeah, nice talk. So for the LES results you showed with non-isotropic grid, did you use the isotropic irrediffusivity for the subgrid model or anisotropic?
No, the question is, what is your turbulence model? Since generally, so these are some our former papers with Piotr Smolarkiewicz and also with Wojtek, since we were using for LES, also for the LES of the dry boundary layer, implicit, generally, if you have a right, if you put too much numerical diffusion in your model, you do not represent properly the what happens in clouds, and you can get by some reason the right answer, like with the stratocumulus stop, since your grid box is much thinner in vertical than the horizontal, you get much higher gradients in vertical than in horizontal, and it corresponds to these properties of the turbulence, which generally works like this. So what I can say, you have to be very careful and you have to understand what your subgrid model does to transport. And this is my only advice. Sorry, it's not very strict and very accurate, but it's not always you do better with the higher resolution, but not always due to right reasons.
So how did you end up calculating or estimating the dissipation rate from the measurements?
If you go to the papers, we have such a paper when we analyze 5 methods and discuss different advantages and disadvantages. And depends on the data segments and on the data. The more robust and what we typically use is the structure functions. In the majority of the situations, it works better. We made a very extensive analysis on artificially generated turbulence, when we could generate some, statistical, functions corresponding to velocity fluctuations, and we applied, these methods. So there is a paper which compares these methods. Of course, you can use anyone you wish. They are the differences. The biggest differences is the factor of 2, which is not that much, since usually you consider the logarithmic changes. of decay dissipation rate. Nevertheless, there are some differences, and yeah, my first suggestion is second-order extraction function.
Yeah, one of the issues with that is dealing with drift in the measurement. When you have inhomogeneous turbulence or intermittent turbulence, could be quite a problem to deal with.
You know, nothing is perfect.
Yeah.
We can either do better or worse. The most important thing is to understand what you are doing, to check several averaging lengths, and to look whether these differences are big or not big, if that is enough or not. So what can I say more?
That's a very nice talk, thanks. I had more or less the same question as Don. I was trying to recall some papers by Lumley and Wingard and Clifford in the 70s looking at the effects of Taylor's hypothesis on the estimation of dissipation, where the large eddies advect the small eddies past the sensor effectively. I guess it's not as much a problem if you're flying through the clouds in an aircraft, but in the helicopter measurements, perhaps it still is a problem, where the unsteady advection by the large eddies broadens the spectrum, but I can't recall the paper conclusions completely.
Yes,
but it definitely affected
I
the
think I know
dissipation
these
rate,
papers, and there was a kind of limit for the velocity variance, for the ratio of the velocity variance to the mean velocity of the flow, through which you could find, you know, whether you are doing well enough. Okay. Generally, at the aircraft, when you fly 60 or 70 meters per second, it's fulfilled. You know, on the again at 20 meters per second, and with this velocity fluctuations of the order of 1 meters per second, sometimes it's pretty well. But I completely agree that for the stationary measurements, it might be a problem when you have the advection with changing wind with the biggest eddies.
I couldn't tell, but would you estimate that your boundary layers that you mostly looked at are weakly unstable or strongly unstable?
You know, for this Azores, it was a PhD study of my student, which is very extensive, and there is a big paper a really long paper in ACP when we step by step analyze two cases and differences. And yes, there were changes in stability. I don't remember the details. Sorry about that.
The detail I'm interested in is if you were flying along wind or across the wind, because if you were flying along wind, the boundary layer makes convective rolls, and you get a very different answer if you're measuring inside the roll or outside the roll.
Yes. So it's especially true above during daytime convection in the over the land when you have strong sensible heat fluxes, but all these cases were cases over the sea with relatively weak fluxes. In post we were flying mostly across the wind, but there were segments along the wind, and we were trying to look for differences, but this was not the kind of this roll structures we have measured. But I am aware of the problem, and it's a very good point. Yes. So I absolutely agree. This over land, it's very important to know. And again, it comes in the autocorrelation functions. If you make autocorrelation functions, then except for the turbulence, you have another maxima related to the cellular structure. If you extend your autocorrelation function, you can get, except for the fast decline in the turbulence scale, then you get maxima related to this, structures and how are they oriented along your track.
Okay, very interesting. We can continue the discussion with over cookies and coffee, but for now, let's thank Simon again for a very interesting seminar.
Thank you very much.